All right, so today we're talking about how things grow, and this is a day one of two. You may have heard the expression, money does not grow on trees. However, money does, in a sense, grow in a savings account. In today's lesson, you will apply your understanding of exponential functions to solve problems involving money and interest. As you work, use the questions below to help focus your team's discussions. How much money does the account start with when it's opened? How does it grow? So, what's the multiplier? And how is the rate written as a percent and decimal form? Saving for college. Suppose you have $1,000 to invest and know of two investment options that pay an 8% annual interest rate. You can invest in bonds, which pay 8% simple interest, or put your money in a credit union account, which pays 8% compound interest. So those are our two different options, 8% simple and 8% compound. Will the option you choose make a difference in the amount of money you earn? Examine the two situations below. So let's look first at the simple interest option. If you invest in bonds, your $1,000 would grow as shown in the table at the right. How does the amount of money grow with simple interest? So we start with $1,000. We get an extra $80 for the first year. We get an extra $80. We get an extra $80. So we are getting the same amount each year. So no matter how long we keep it in there, extra $80 each year. By what percent would your balance have increased at the end of the fourth year? So at the end of the fourth year, if we add in another $80, we'd be at $1,320, which means $1,320 compared to the initial $1,000 we started with. That's 1.32 or 32% growth after 4 years. All right, so that's what we're comparing. So this is our simple interest. Now, what about compound interest? Instead, if you invest your $1,000 in the credit union at 8% compound interest, that is compounded once a year, its value would grow as shown at right. How is it growing? So here we got $80. But then in the next year, you'll notice that it wasn't just another $80. It was actually $86.40. So the amount that we're adding each year is going up. So not only is our balance going up, but the increase to our balance is going up. So you earn 8% of the previous year. Explain how compound interest is calculated. So what we're really doing is we're showing something that is growing exponentially. So if you look at the simple interest, we were doing repeated addition. When we are doing compound interest, we're doing repeated multiplication. So this plus 80 plus 86.40, that tells us that it's not repeated addition. Why is there $1,166.40 in your account at the end of the second year? We took 8% of the 1080, which was 86.40. So we did 1080 plus an additional 86.40 and got 1,166.40. Now, if you compare that 1,160 to 1,166.40 after 2 years, not a huge difference, right? But if we were going to keep this money and try to save it for college, we'd be saving it for many years, not just 1 or 2 years. So D, what will be the balance of the credit union account at the end of the fourth year? So each time, what we're actually doing is multiplying by 1.08. Multiplying by 1.08. You keep 100% of what you had, and you get an extra 8%. So at the end of the fourth year, you'd be at 1360.49. So we would put that here as well. And what percent is that? So 1360.49 over the initial $1,000 is approximately 1.36 or a 36% growth after 4 years. Whoa, YEARS, sorry about that. Which type of account? A bond with simple interest or the credit union's compound interest grows most quickly. The compound interest grows most quickly, especially because we're talking about two types of interest that were the same percent. So we were comparing, apples to apples. They both had the same amount of initial value and they both had the same percent. If those things are the same, compound interest is going to be better. Now, there's a question here about graphing. It says, starting with $1,000, show on one graph how each type of investment, simple or compound, grows over 8 years. Use a different color to graph each situation. What happens to the amount of money during the year? So during the year, so if you're at year 6 and 52 days, it's the same as when you were at day 6 and 1 day. So it stays the same all year long. Assume that the interest is added at the beginning of a new year. What happens to the amount of money at the start of the next year? That's when the increase is added. All right. How is this shown on the graph? So when you go to graph one of these, you would start with a closed circle on the left and then a dash for the year, because the whole year you stay the same. Well, then at year 1, you would have to have an open circle on the day that starts year 1. And then the next one would have to go up. So our next one was $1,080. So it should be pretty darn close on this one. And then it's going to go for the year and then be an open circle. So each one of these is going to have a single day when the interest gets added. And so the previous year has an open circle because that number is not included, but it's like the cutoff day. And then the next one starts with a closed circle because that's the day where the new amount is added. So we have a closed circle on the left and an open circle on the right. So if we were going to graph this now, I have one that's all filled in. And I don't have the open and closed circles all the way just because they were a little bit too close to each other. But what you can see is that, sorry, wiggling that around a little bit, is that the yellow ones are the ones on the bottom, and those are your simple interest amounts over the different years. And the sort of orange-red color is above it because it's growing faster. Every single one of those should have a closed circle on the left and an open circle on the right on the day that the money shifts. All right. So the amount of money in an investment account earning simple or compound interest, such as the situations in problem 833, can be modeled with step functions. Writing equations for step functions can be very complicated. However, we can model the step functions with continuous functions that we're already familiar with. From now on in this course, we will use continuous functions to model situations unless indicated otherwise. So the concept, clearly we know that 2.5 years is the same as 2 years and 1 day is the same as 2 years and 364 days, but a continuous function is an easier model. So if we're going to model question 833, it says, think about growth and the starting point in the investment accounts earning simple and compound interest. Model each of the 2 graphs of step functions you created with an equation. Let y equal the money in the account after X years. Check that your equations produce the same values in the problem. So the simple interest one, which would be arithmetic, right? Because it was repeated addition, it's going to look like a slope-intercept form. So we would have 80x because we're gaining $80 per year, and the initial amount is $1,000. Then if we had the compound interest, that one we said was exponential. So it is going to be y equals the initial value of $1,000. Our multiplier was 1.08 because we keep all of our money and an additional 8%, which is the 0.08, to the x power, and that is our exponential or repeated multiplication form. Use your models to predict how much your original $1,000 investment would be worth at the end of 20 years. So let's just say you have a grandparent that's going to put money in the account when you're born, and you're allowed to take it out when you turn 20, and they put $1,000 in. So if they put it into a simple interest account and you do 1,000 times 80, right? That's your interest. You're going to get $80 of interest 1,000 times. No, that's not right. I don't know where I came up with plugging in 1,000. That's a 20 years. You're going to plug it in for 20 years. You don't get it 1,000 times. That would be several generations. 80 times 20, going to be $1,600 earned in interest plus the initial 1,000. So this person is going to walk away with a nice $2,600 for their grandparents' $1,000 investment. Now, if the grandparent had found a compound interest, initially put in $1,000, 1.08 for the multiplier, but raised it to the 20th power, every one of those 20 years, you'd be getting 8% on whatever you had the year before. So 1.08 to the 20th is approximately 4.66. So I'm going to switch my equal sign to approximately equal because I had to round this. So this person is going to get approximately $4,660.96 20 years later. So that's a $2,060 difference, guys. So finding that compound interest, if you're doing something over a long period of time, huge change. Why are the equations considered a model of a representation of the actual behavior? This is a model. It's not a good representation big picture because I could plug in 4.5, right? I could plug in 4.5 years and it would tell me a value after 4.5 years, but the bank wouldn't actually give me anything different at 4.5 years than it would at 4 years and 1 day. So it shows growth between years, which doesn't actually happen. What is the advantage to using the model to making predictions? It's a lot quicker to graph and it's a lot quicker to calculate. And if we use just the logical part of our brain and say, great, if I've had that in there for 5 years and 7 months, I'm only going to plug in 5 because I won't get credit for the 6th year until the actual start of the 6th year. What interest rate would the bonds with simple interest need to earn so that you would earn the same amount in both accounts after 6 years? And what about after 20 years? So this is a little bit tricky. So what I'm going to do is I'm going to show you the work that I already have done out and explain what I've done. So on this one, I had $1,000 at 8% for 6 years. And it was $1,586.87 as my, end of 6 years. This is what I'm walking away with. So you needed to come up with $586.87 in interest, right? Because that's the amount that they earned over and above their starting $1,000. Well, if I took that $586.87 and divided it up over 6 years, I would need some sort of interest rate that would give me $97.81 per year, which would be 9.78%. So if I take just a step back, the compound interest was at 8%. If I want to earn the exact same final dollar amount, I would need to find a simple interest rate of 9.78%. So both of them are at 6 years, but in order to come out with the same amount of money, the simple interest rate would need to be significantly higher. At 20 years, you're going to see an even bigger difference. I did the 8% for 20 years and found that this person walks away with $4,660.96. That means they made $3,660.96 in just interest. If I divide the $3,660.96 by 20 years, I would have to find a simple interest rate that was going to give me $183.05 per year. That's 18.3%. I think you're going to be pretty hard pressed to find any interest rate anywhere near 18.3%, unless it's one of those interest rates you don't want, like a credit card, to be that high. So 20 years at 8% earned us a bonus $3,660.96 in interest. If we wanted to get that same amount in interest divided up over 20 years, I would need to find a simple interest rate of 18.3%. Good luck. All right. So the last one that we have here, the last page, question 835, let me slide that down so you can see it, says, examine the two types of investments, simple and compound interest, through other representations. So consider, consider the sequence 1,000, 1,080, 1,060, 1,240. Is the sequence arithmetic, geometric, or neither? So we would say because it is simple interest, because it is repeated addition, plus 80, it is arithmetic. The multiplier, or I should say the growth pattern, is plus 80. So it's a sequence. We're going to start with T of n because it's a sequence. we are going to say it is 80n. That's our plus 80, plus 80, plus 80. And our initial value, if we worked back one spot and went take away 80, the 0th term would have been 920. So plus our 0th term, 920. Consider the sequence 1000, 1080, 1166, and so on. Is this arithmetic, geometric, or neither? We found this one to be geometric. So we had a simple interest was arithmetic, compound interest was geometric. That's because on this one, we did multiply by 1.08, multiply by 1.08, multiply by 1.08, and so on. Write an explicit equation for this sequence. It says sequence, so we're using T of n. The multiplier 1.08 is what's going to go in the parentheses to the nth power. And we need our initial value, which is the one before the 1,000. So if we went here, we'd need to divide by 1.08 to get that the initial value was 925.93 for the equation. We're not talking about walking into a bank. We're talking about what does the equation look like in order to be able to graph it or use it. So this is 925.93, 1.08 to the nth. My handwriting was a little smushed there. How would the sequences in parts A and B represent investments, simple or compound? So the arithmetic was simple interest, the geometric was compound interest. Think about the graphs of both. Can your knowledge of the shapes of the graph help you choose which investment to make? So an arithmetic graph would be the simple interest graph. It would show linear growth, right? It would show a straight line and have a constant rate of change. The geometric would be our compound interest. It would be curved and it would grow more quickly. It would overtake the arithmetic line. Eventually, the geometric would have a larger investment. So if you have a choice and all other things are considered equal, the compound interest is going to be better than the simple interest.